All right, welcome to part two of today's class. Um, just following on from what Bob presented, I wanted to just highlight a place where I used to live called Sudbury, Ontario, and I encourage you to look it up because what they used to do was roast sulfide ores there in the open air back in the latter part of the 1800s and into the 1900s. And as a result, basically all the vegetation around Sudbury. There were other reasons too, but basically all the vegetation around Sudbury was killed, and it was a wasteland. In fact, they used to test lunar modules in Sudbury as a analog for the lunar surface. But if you go to Sudbury now, it's really green, and it's one of the most remarkable examples of recovering from adverse mining effects that there is. There's still lots of active mines in Sudbury. They're done very differently now, but it's really, in fact, the town of Sudbury won a United Nations award for their regreening efforts. It's quite remarkable.
Cool.
Okay, so now we're going to talk about critical minerals and metals. So what's a critical mineral? So they're defined as minerals that are deemed critical to both the economic and national security of the country. So what each country defines as a critical mineral depends on their access to resources and how much any particular metal or mineral is required by their industry. And so these things are really important for specialized application, but may be at risk for global supply disruption. And we'll go through some examples as we go through today. And so a lot of what is in this lecture comes from an American perspective, but there's some Canadian perspective sprinkled in and a couple of European perspectives as well. So in 2018, you got to see how I can get rid of this thing here. In 2018, the US developed their first critical mineral list with 35 commodities, and now it's up to 50 commodities. And as I say, how each country defines those can be different. So the United States lists all the rare earth elements as critical minerals. In Canada, they just refer to them as rare earth elements as one critical mineral, even though there are 17 rare earth elements. So just some screenshots of minerals in the news. So you probably heard that, and one can argue about the political winds behind it, but the United States and Ukraine have signed an agreement to extract and exploit Ukraine's mineral resources, if and when, of course, the war is ever over. Bob showed the gold price. I updated the gold price yesterday, so it closed on Friday at $33.73 an ounce in US dollars. It's been a remarkable rise. Back in the 80s and early 90s, it was a shocker when gold reached $800 an ounce. Greenland's been in the news for obvious reasons. Some leaders in some countries want to take over Greenland. Why would they want to do that? Greenland has a deposit, which is probably the second largest rare earth element deposit in the world. It's unexploited, obviously. It hasn't been mined yet, but the potential in Greenland for mineral resources is huge. And unfortunate consequence of global warming, as the ice melts in Greenland, more and more rock is being exposed to discover more and more metals. Also recently, in the last few years, with geopolitics becoming more fraught, China is, as we'll see today, has a major supplier of many critical minerals. And so they have the ability to say, well, we're just going to stop providing them to the global market. And so that gives them a lot of clout when they're dealing with tariff negotiations and so forth. This paper was published just in the last few days, and I found it yesterday, I guess. And what's really interesting is this study was done, and what they did was they did a statistical analysis based on the composition of ores being mined in the United States at the present time. And if that material if the critical minerals were actually extracted from that material, the United States could largely, if not completely, satisfy the entire critical metal needs of the country. The problem is we can't necessarily extract at an economically viable way all the metals that are in a particular volume of rock. And so, as the paper says in the abstract, what we need are policies and technological advances that are going to enable byproduct recovery in a much more efficient and cost-effective way. But nevertheless, I think the take-home message is that if a country plays really hardball with these critical minerals, there within any jurisdiction, there are ways in which those challenges can be overcome. So the Congressional Research Service put together their critical minerals list. And what we really need to decide is what is a critical mineral. And so it's a non-fuel mineral essential for use and faces considerable supply chain vulnerabilities, as we've already said. And so as an example, lithium is used a lot or has been increasingly used as we've come to a more technological and green economy. So in particular, lithium-ion batteries for electrical vehicles and so forth. The rare earth elements are increasingly being used in a wide variety of technologies and so forth. And we'll talk more about the rare earth elements. They're a particular favorite group of metals of mine. And so demand for these, as we advance and become more technological in things like healthcare, transport, power generation, consumer electronics, getting away from fossil fuels, having more and more sophisticated defense technologies and so forth, then we need more and more critical minerals. And so as a geologist, I find it odd that we discuss critical minerals because most of the things on the critical minerals lists are actually critical metals. And so you could say, aren't critical metals really just critical minerals, just really critical metals? There are some exceptions like bauxite, graphite, phosphate for fertilizer and so forth. But generally speaking, yes, critical minerals are just critical metals. And so Bob wrote this, why doesn't the Geological Survey know the difference? And you'd think they would. And it's because I think it's become a buzzword. Critical minerals is the buzzword. I mean, it's interesting. Economic geologists have been working on these metals for decades, generations, but weren't clever enough to come up with a buzzword. And now there's a buzzword, and incredible amounts of money are being thrown into critical minerals research in lots of different jurisdictions. And feel free to, yes, Clint.
It's okay. I mean, minerals, it winds up being used to describe all kinds of things, including oil. And, last time I looked, oil wasn't very minerally, but in Texas, we refer to it as that.
Yeah, to a geologist, oil is not a mineral, but I suppose people refer to mineral oils. But yeah, we can get into the definition of a mineral. I think Bob's going to do that in a subsequent lecture. Okay, so here's a little video.
Critical minerals are the materials that all of our clean energy technologies are made from. They are used in electric car batteries, wind turbines, electric grids, things like copper, lithium, cobalt.
They play an important role in helping our technologies be more efficient. Wind turbines more powerful or lighter. Electric cars can have longer ranges.
A lot of these minerals are already in use for a number of different things. Copper, for example, we use in all kinds of electric applications. And what we need it for is huge expansion of the grid. So what we're using it for is some of the same things we've always used it for, but we need a lot more of it.
There are enough resources in the ground, but the question is to translate those resources into production with adequate investment. As we accelerate energy transitions, demand for these minerals can grow quite rapidly. So there are some risks of short supply might emerge.
And a supply disruption for critical minerals does not directly affect people driving electric cars or people using solar panels at home. However, supply disruptions have an impact on the future manufacturing capacity of all clean energy technologies.
If we don't have the adequate supply supply of critical minerals, it can make our transition either slower or more expensive, which is the risk we cannot have room to take.
Let's see. Okay, go forward. Get my laser pointer. Okay, so some fun facts from the natural resources of the United States. So for every job in mining, in metals mining, about 2.3 additional jobs are generated, which is a pretty good multiplier. In oil and gas, for example, it's only about 1.6 jobs. So the U.S. is 100% reliant on foreign countries for about 17 critical and strategic minerals. Although, as I said, if the right technologies exist, the U.S. could recover all those metals within their borders. The rare earth elements are a group of 17 unique metal elements that are critical for manufacturing high-tech, defense, renewable energy, and everyday items. And we will talk some more about rare earths. There are lots of critical minerals that the United States, or Canada for that matter, is not producing. In this document, they said that the U.S. is dependent on China, which produces 97% of the rare earth elements available in the world today. It's not that high at the moment, and we'll discuss that in a second. The U.S. imports a lot of minerals from foreign countries, about $8 billion worth, and to contain metals, not including all those that we could recover with increased technology, is about $6.2 trillion worth. And that's that we know about. In some of the work that I do is in mineral exploration using geochemistry, and the challenge for mineral exploration is that most of the near surface and rich deposits have been found. And so we have, as Bob alluded to, with the depth of gold mines, we have to go deeper and deeper to find more and more metal resources. But they're there. Okay, metals are really important for national security. So Department of Defense estimates that they use about 750,000 tons of minerals for things like jet engines, night vision goggles, military aircraft, and armored vehicles, and a wide variety of different metals. Just as an example, night vision goggles use 3 different rare earth elements. Then I found this graphic from the Congressional Research Service.
Not to get technical, but I'm not familiar with rhenium and how's that used in jet engines?
So rhenium is, if I'm not mistaken, it's a platinum group element, and actually I'm not sure what it's used for in jet engines. That's a great question.
Yeah, you're probably going to run across quite a few element names that folks haven't heard of,
exactly.
And the question like that. That's a very good question. I have no clue how it's used either, but one can imagine they're using it as some kind of an alloy, for whatever. But
yeah, it's an extremely rare element on Earth.
Yeah.
Anyway, so the chart, the figure on the bottom right there just shows that to make an F-35 requires, I'm going to go to kilograms, roughly 425 kilograms of rare earth elements. To make a submarine, we need about 4,000 kilograms, or 4 metric tons of rare earth elements to make one submarine, which I thought was pretty interesting. So heavily used. Lots of critical minerals are used in medical devices. So things like CAT scans use tungsten, copper, lead, silver. It says chlorine, I would say chloride because chlorine's a gas. Aluminum and gold. X-rays use thulium, yttrium, and gadolinium. These are all rare earth elements. And there's lots of different rare earth elements used in different lasers. And the other thing, gadolinium is also used as an MRI contrast agent. And it's really interesting because some of the work I do is looking at rare earth elements in groundwaters and rivers. And especially in Europe, you can see excess gadolinium in the waters because of leaching of medical waste into the environment, which is pretty interesting. And then lots in consumer electronics. So you can see that, in computers and iPods and iPads and iPhones, they basically use, there's an image here that these devices use large numbers of critical minerals for their various components.
Hi, Matt. I was just wondering what are the main environmental risks? I mean, you mentioned gadolinium in the environment, but what are the risks associated with these minerals?
Yes, so that's a really interesting question. And to put it briefly, the epidemiological studies on the risks from the rare earth elements has simply not really been done. It's an area of increasing concern. So there are people starting to study this, but just those studies haven't really been done for the rare earth elements. There is some fear that they may be carcinogenic, but there's no evidence to support that as of yet.
Yeah, my understanding of the rare earths is that they have a relatively low toxic profile because they just aren't that common. It's like you think about arsenic, and things like that as mercury, lead being very toxic. I haven't heard about rare earths being toxic yet, but
as I say, that's because the studies haven't been done. It's we just had a master's student who graduated, and that was part of the motivation. Was the study was to see, are the rare earths escaping from a rare earth mine in Canada into the surrounding environment? Turns out not really. Okay, lots of critical metals used in renewable energy, things like wind turbines, solar technologies, hybrid vehicles, and energy efficient light bulbs. And as again, you can see light bulbs, europium, terbium, and yttrium. Again, these are all rare earths. Hybrid vehicles use, platinum is a platinum group element, obviously, but dysprosium, lanthanum, neodymium, and praseodymium are all rare earths. Solar tech uses lots of silver, copper, and gallium is used a lot, tellurium. And there's an image here at the bottom for a wind turbine. And you can see that wind turbines use, unfortunately, this is imperial units, but difference between imperial ton and a metric ton is not that different. So 1,200 tons of concrete in a windmill, but 300 some odd tons of steel, or 5 tons of copper, and 2 tons of rare earth elements. So, about half the amount of copper is a rare earth element.
That's hard to believe.
Yeah, I forgot to put the source of that, but anyway.
Yeah, but
yeah,
they use a lot.
That is a lot. You're right. I'll have to check that. Okay, so the idea is that demand for critical minerals is going to increase. And this is because so much of these metals are needed for the kinds of technologies that we're using to move away from fossil fuels. Although I will point out that the United States just canceled a major offshore wind project that was 80% complete and has now been, well, not canceled, but put on hold, which is unfortunate. So the International Energy Agency, the IEA, estimates that mineral requirements will increase 4 times by 2040 if we're going to limit global warming to 2 degrees C, although some feel that limit's not really viable. Or if we want to meet net zero by 2040, we're going to need a 6 times increase in the amount of metals that we're producing. And so wind and solar plants require many more minerals than thermal power plants or fossil fuels. And so solar voltaics require lots of copper and silicon, and as I said in the previous slide, gallium. Wind turbines require zinc, but lots of manganese, nickel, chromium, molybdenum as well. And so the renewable energy depends on developing electricity storage to address the fact that solar and wind energy are not always act, or not, the wind's not always blowing and the sun shuts off at night, at least depending where you are. And so lots of lithium will be needed, except that, as I mentioned later on, technologies are changing all the time. And so there's some people who think that actually lithium doesn't have a long-term future in battery technology, but we'll get to that. So the other thing that we're doing is we're transitioning from the internal combustion engine to electric vehicles. And I've been actually, given my age, I've been astounded at how fast the electrical vehicle transition has been taking place in many countries, particularly in China, for example. So the typical electric vehicle uses about 5 times as many metals as an internal combustion engine. And so there are about 1.5 billion vehicles on the road in the world right now, each requiring about 160 kilograms of metal. And so even if we just replace 10% of these each year, that would require 24 million metric tons of metal per year. And so if we think about things like lithium right now, annual production is about 100,000 tons for lithium, about 25 million tons for copper. So if we're going to upscale our metal requirements, you can see we're going to need to find more and more resources and have more and more mining rather than less, as many would like. And so this is a really interesting chart, and what it does is it takes the production as of 2017 for a bunch of different metal resources, and then on the right-hand side we have the estimates for the demand, and these are in kilo metric tons. So in other words, the amount of lithium produced in 2017 was 43,000 metric tons. It's estimated that the annual production would have to be 415,000 metric tons in 2050. So you take the first number, you take the 415 divided by the 43, and what that means is that a 965% increase in the metal demand. Okay, and so you can see as we come down the chart, that increase in metal demand changes depending on the metal. And once we get below 100%, what that means is the demand in 2050 will actually be lower than the production in 2017. Now, it's a very interesting chart, and I was quite surprised at it because other people have quite different estimates as to what the demand is going to be, and this is the problem with trying to extrapolate based on today's technologies what we're going to need in 25 years' time. And so this is from a different source, and what this shows in the dark green is the base production of copper, and you can see that copper production is anticipated based on what we know is in the ground now, is going to peak around about now, actually. The red is probable projects, which could come on stream, but what you see is by 2050, the metals that we know of in the ground, we're just not going to be able to produce what we likely need. And that's the orange line, which is a projection of future demand. And then even with possible projects, according to this estimate, we're not going to be able to produce as much copper as we're going to need. And so that's going to require changes in our technologies, changes in our ability to extract metals from rocks, and things like that. And perhaps going deeper and deeper to get to undiscovered deposits.
You have a question from Tom.
Hey, Tom.
Do you know what makes up these different kind of projects? So the possible projects and probable projects, what those kind of, I guess, different projects represent?
No, that's a great question. So when we use the term ore deposit, what we mean is that the metals can actually be extracted. What's the word I want? My brain's just gone out me. Economically, they can be extracted by making a profit, which is ultimately what companies need to do, is make profits for their shareholders. So it's profitable. And so the green ones are the active producing mines, and the probable ones are things that are likely to come on stream soon. And the green represents deposits that or they're not deposits, they are showings or occurrences of copper that with more drilling, with more work, we might, as Bob mentioned earlier, we might convert from a known occurrence into resources and then into reserves. Does that answer the question? Okay. So here's a map of countries that account for the largest share of critical raw materials. And I have to confess that as a Canadian, I'm distressed that Canada is not on there. Although Canada has an awful lot of metal resources, as Bob alluded to earlier. And the fact is, we're not as good as, I guess, at putting them into production. Canada has fairly strict environmental rules. Nevertheless, what you can see from this is that some countries have one or two metals or critical strategic resources that they have a lot of. So the United States, for example, produces 90% of the beryllium and 73% of the helium that's used in the world, which is interesting. Brazil has 90% of the niobium. And what you see is the list from China. China has immense resources and has put the money into the production of those resources to dominate global supply chains with a large number of critical metals.
And not very oppressive environmental regulations.
No, their environmental regulations are somewhat lower than, say, in North America. I should point out that I'm hoping to get a guest speaker to talk about mining and indigenous peoples. Even though Canadian companies operating in Canada have very strict environmental rules, unfortunately, some Canadian mining companies and American mining companies, when they operate in other countries, do not adhere to those rules, which is unfortunate. There was actually a bill put before our parliament to enforce Canadian companies to use Canadian environmental legislation anywhere they operated in the world, but it was defeated by lobbying from a mining association. There you go. Yeah, that's good. Sorry, I thought I had another slide in there. Okay, so the rare earth elements. So the rare earth elements are a really interesting group of elements. If you look on I should have had a periodic table on here, I apologize. But there's 15 rare earth elements that pop out of your periodic table from lanthanum. They're called the lanthanides. And then we include yttrium and scandium as rare earth elements. And what's really cool about them is they behave very chemically similar, except they have slight differences as a function of the number of protons, the number of electrons they have, and so forth, their electronic configuration. But you can see this is just a chart showing all the different, well, not all, many of the different uses of the rare earth elements. And I'm not going to go through them all. Nevertheless, you can see that there's an awful lot of them. And so China dominates rare earth element production. So this is just a fancy chart showing, yeah, China has roughly 69–70% of global production of the rare earth elements. You can see the United States back in '95 produced some. Then the mine that was producing them, Mountain Pass, went out of production. And the US sort of pops back in again a little bit and then disappears again around 2015. So the mine went out of production again. And then more recently, the US has got a reasonable chunk of the rare earth element supply because Mountain Pass is back into production. And this is just looking at the same kind of data in a slightly different way, just perhaps a less confused way. But the United States at the current time, as in 2024, produced 11.5% of the rare earth elements produced globally. So in 2024, Mountain Pass mine produced 45,000 metric tons of rare earth element oxides. And again, this is another chart showing basically the same kind of things to 2020, but production and demand for rare earths was relatively low. The earlier part of this, the latter part of the last century and this part of this century. But they've become essential for evolving technologies, particularly in electronics and magnets. And so China increased its production beginning in the mid-1980s and became the major producer. And as I said, Mountain Pass went out of production, which dropped the United States off the major producers of rare earth elements. And the interesting thing is that the deposits that the Chinese are mining are quite different from the deposits that are mined in other parts of the world. In China, there's these, they're basically soils which are heavily enriched in rare earth elements. And so they mine those, and as Bob said, not in a very environmentally friendly way. So cobalt's another one that's interesting. So the Democratic Republic of the Congo in 2021 was responsible for 72% of the cobalt that was mined in the world. And you can see no other country has more than 5% of cobalt production. And so why is that important? Well, cobalt's used a lot in modern technologies. And the problem is that the Democratic Republic of the Congo, I have some stats over here. So, well, probably the most important one is that the DRC ranks 82 out of 83 in terms of mining risk. In other words, for foreign companies to operate in the Congo to produce cobalt, it's a highly risky prospect. And most mining companies are fairly risk averse, or at least their shareholders are. But you can see some of these other stats that the Congo is 151 out of 159 countries based in their Human Freedom Index and so forth. And so the point of this is that where we get critical metals from is really important, because from a couple of different perspectives. One is from an environmental perspective. Are those countries operating in an environmentally friendly way? How are the human resources being treated? In the DRC, the mining is very primitive, and people are not treated well in terms of how they're mining, and it's not very safe. And then the government of the DRC has traditionally not been very stable, and so this can disrupt global supply chains. And so we have an over-reliance on the DRC for cobalt production globally. In other cases, minerals have a diversified supply base. So for example, Chile is a major producer of copper, huge copper mines in Chile, but it produces about 28% of the global copper supply, and 12% for Peru. Lithium, for example, Australia is about 50%, China's about 15%, and those are from hard rock mining. Chile produces about 30% of the lithium from brines. But I added a chart here to show that it really depends on where you live as to what's perceived as critical and strategic and so forth. And so this is just for different weapons manufacturing in Europe, which of course in the context of Russia invading Ukraine is very important. The Europeans are massively ramping up production of weapons and military vehicles and so forth. And so it's a little hard to see, but you know, some of the very high risk things include things like aluminum and graphite for all of these things, because Europe doesn't have ready access to those kinds of materials. And so it just highlights that where you are influences what's critical. And so will technological advances change demand for certain metals? And the answer is yes. Maybe we will produce cobalt and nickel-free lithium batteries, and in which case our reliance on the DRC for cobalt will decrease. High energy density batteries are needed for vehicles. but not used for stationary energy storage. And the interesting thing is that in just in the last couple of years, I've been seeing increasingly large number of research papers and so forth looking at different kinds of battery. And so actually sodium ion batteries have been around for a while, but their interest in them has increased in the last couple of years. And the reason is they're safer than lithium. They're cheaper to produce because sodium is everywhere. We could get it from seawater, for example, and therefore there's a less risky supply chain. And so will the increased demand for lithium be the same in, say, 10 years' time or by 2050 and so forth? And as technology changes, as we transition to a more green economy, mining industry is well known for boom and bust cycles, and these are likely to continue. So these are all things that we need to be aware of. What about in your house? So what metals are used in your house? Bob showed a figure earlier, but in terms of building the house itself, steel's used a lot for support, for roofs, for rebar, and everything else. But actually, more and more houses are actually being framed in steel. So the images of the picture from Western Australia, and in Western Australia, you're not allowed to build with wooden frames anymore because the termite population is so big in Western Australia. Wooden houses just don't survive. So the construction's all made out of steel. Lots of copper is used in houses, lots of aluminum. Okay, and then, as I've sort of alluded to, but with semiconductors and chip technology, we need more and more metals. And so what's deemed as being critical as we transition to a much more technological society, what's deemed as being critical has also changed. And so you can see that in the 1980s, only 12 elements were really deemed as critical. By the 1990s, we added another 4 elements, including titanium, tantalum, tungsten, and beryllium. And then by the 2000s, we're now upwards of 60 elements that are considered critical, including all the rare earths. So here's the rare earths down here at the bottom, popping out of lanthanum on the periodic table. And just as an aside, this one here, promethium, is white because it doesn't occur naturally. It's too unstable. And then yttrium is over here, and scandium is here. Okay, so you can go to this resource to get the list of the USGS critical minerals. It's being updated this year, but right now you still see the 2022 list. It includes things like barite and fluorspar, which is fluorite, and graphite, but everything else is really critical metals, as I mentioned earlier. This is Canada's critical minerals strategy or list, done in the shape of a maple leaf, which is sort of emblematic of Canada. And as I mentioned earlier, you see the rare earth elements, all 17 of them, not scandium. So scandium's a rare earth. But anyway, most of the rare earths are just considered one spot on here. So really Canada's list is much longer if you individualize the different rare earths. You can see mostly metals, except graphite. Let's see, phosphorus. Where's phosphorus? Potash or phosphorus. It's not a metal. So we have to think about the supply chain. And so the supply chain involves the extraction. Where are the metals extracted? Then where are they processed? Where are things developed? Where is the end use? Where is the materials that are gone into some technology? Where are they being used? One of the things that is changing how we think about metal supply and extraction is increasingly we are recycling metals. So, for example, a lot of aluminum is recycled and a lot of steel is recycled. Supply chains can be vulnerable if they lack the diversity and capacity to satisfy the needs of any particular jurisdiction. And so some of the things that limit the diversity of metal supply or extraction and processing is that these things may be done in only a few locations. So, for example, up until this year, that Mountain Pass rare earth element deposit in the United States, all of their material was being sent to China for processing. Given the geopolitical issues between the United States and China, Mountain Pass is now trying to set up processing plants within, or a processing plant within the United States. And so other factors that can limit things are things like access to indigenous lands, which is a particular issue in Canada, for example. Many First Nations people in Canada are anti-mining. Some First Nations in Canada are pro-mining, and some mines cross Indigenous jurisdictional boundaries, so leading to potential conflicts and so forth. National and state parks, technological challenges, export quotas. So, for example, China saying, no, we're not going to export a particular metal at this particular time. Environmental impacts, geopolitical volatility, which I mentioned with respect to, say, the DRC, market volatility, boom and bust cycle of metals, and capital requirements. So who's going to fund the extraction of metals? And so we can think of the vulnerability in terms of production, which I've sort of already talked about, but this is an interesting map of the world that just shows with these bars, right? So Congo, 70% of cobalt production is in the Congo. 70% of graphite production is from China and so forth. You can see Australia is very important for lithium production from spodumene, from hard rock mining, for example. Whereas Chile, it's from brines. Canada's got a little bit of graphite. Woohoo! Canada's on there. And then in terms of processing, so Canada processes a lot of nickel, but it doesn't show up on nickel, even though Canada does produce a fair amount of nickel. It doesn't fit in the top four, and so it doesn't have a bar on this plot, but lots of nickel processed in Canada. And so, for example, nickel will come from other places in the world to Canada for smelting.
So Clinton's got a question.
Sure, go for it.
No, just going to mention there's graphite ore bodies are very interesting. We've got one in Texas. It's not in use, but it's I've actually talked to somebody whose brother used to work there and came home covered in graphite, and it's made them very slippery and hard to use doorknobs.
Yes, indeed.
Fun fact.
Yeah. Fun fact. Anyway, so yes, China's one of the top producers for the rare earths, and as I mentioned earlier, Mountain Pass sent their rare earths to China for processing. And so this is a nice chart that shows, which Bob mentioned these components earlier, but we have the extraction component, the processing component, the components where what are things being made, and then their end use technology. So what are they being used for? And recycling and reuse feeds into all of these, although you can really, the recycling arrow should be at every step of the process. But all of these steps happen in different jurisdictions and can have different risks or opportunities associated with them. So as I mentioned earlier, if we had the technological advances, the United States might be able to reduce its reliance on other countries for critical minerals. Same with Canada. We have huge resources that are just not being exploited. There's several large rare earth deposits in Canada which have not gone into production, just as an example. And this is an interesting graph from the Department of Energy in the United States, which I like. So the left-hand one is the short-term risk, and the right-hand one is the medium-term risk. And so on the y-axis is the importance of the metal to energy, and on the x-axis is the supply risk. And so you can see the red is it's very critical, orange is near critical, and green is not critical. So there's lots of manganese, there's lots of aluminum in the United States and so forth. So these are not hugely critical. Look over here, cobalt, gallium, graphite, indium, neodymium, which is a rare earth, terbium, which is a rare earth, dysprosium, which is a rare earth. And then as we project into the future, what comes up into this top right corner are things like lithium and nickel. So it just gives you a sense of why do we need things, and then how risky is it to produce those things or to access those things.
You may have answered it with this graph, but I just wanted to know if you had any personal opinions on what ones were really critical and big issues going forward.
Oh, I think I have a graph coming next. Yeah, germanium and gallium are big ones, from which are largely supplied by China. The rare earth elements, obviously. I mean, right now the United States production is from one mine, and there's all these risks of diversity with one mine. And then cobalt. You know, will we be able to develop the battery technologies fast enough to reduce our reliance on the DRC for cobalt? Although I have to say I have two thoughts in my mind about that. Yes, it would be nice not to support a country that's has poor environmental and human practices. On the other hand, if we stop buying metals from the Congo, that reduces their income, which is going to affect the people as well. So there's lots of different factors that have to come into play here.
A lot of that income might end up in European accounts in Switzerland or something, but
Yeah.
that's another issue.
Well, that's very true too. Yeah. Yes, perhaps we need a revolution in global banking as well as in technology. So this is just an interesting chart for gallium, because China has threatened to restrict gallium and germanium. And so on the y-axis of the plot here, it just says it's the net decrease in the U.S. gross domestic product in billions of dollars, depending on, and the y-axis is the percent that China restricts their exports. And so if China restricted 100% of their exports, it would impact the American economy by $3.1 billion, because they're the major suppliers, and it's hard to then suddenly, as Bob said, it takes 10 times as long to open a metal mine as it does to open an oil field. It can take 10, 20 years to start a mine. And so it becomes very hard to pivot to other supplies of critical minerals if one country has the dominant supply and threatens to cut that off. And then just to end with a joke, so Kyanite's talking to calcite. So then he says, "I thought you were a carbonate."
Unknown pop.
And iridium's looking on rather skeptically. So they laugh. Iridium doesn't get it. He's a bit dense. And so I just put on the side here the density of those different materials. So iridium is a critical mineral in the United States. It's not in Canada, but it is. But you can see its mass in grams per cubic centimeter is way higher than kyanite and higher than calcite. So, yes, humor. Just as an aside, one of the ways we can determine large meteorite impacts on Earth is at the KT boundary, for example, there's a layer of iridium, because iridium is so rare on Earth, but can be enriched in things that hit us. Okay, and that's it.